Hi, and welcome to question 11 of the 2023 Junior Cert Higher Level. So as always, if you want a copy of the notes, just send me an email at shanetroy@gmail.com. Like and subscribe to get access to more playlists. So question 11 is kind of coordinate geometry, just kind of a bit of algebra in there. It's a bit of a mix of stuff, lots of words, which can be problematic. So let's go slow and read through it. Never forget to underline anything you think is important and just to get a good understanding of what the question is saying. That may involve reading the question 3 or 4 times or more, and don't be embarrassed. The times that I make errors, the many times I make errors, are because I read the question too fast. So it starts off here, 30,000 people, so that might be important, went to a football match in Star Stadium. Now, cool as football. It's cool that the stadium is called Star, but they don't matter. And it says after the match, so that looks important, the 30,000 people left the stadium at a constant rate. Now, the second I see constant, I'm thinking slopes. Okay, linear models have constant slope. Okay, so that's a feature. The graph below shows P, the number of people still in the stadium, T minutes after the end of the match. So as the match ends, there'll be a few people will leave before, I'm sure, but usually everybody leaves at the end, and it's going down at a constant rate. I guess the exits can only handle so many people, whatever it is. Okay, now the reality of things, I'm sure, will be a much more like erratic thing, and there'll be a tail off at the end as somebody hangs around way too long. But this is a scenario we're just going to go with it. Okay, so P is the number of people. Okay, T is time. So there's two unknowns. Okay, as it stands. Now we might be able to find out more information. And this graph can be modeled. This is a kind of a graphical model, but can be modeled mathematically with a linear equation. Okay. So it says here part A, now the graph says number of people in Star Stadium. It starts off at 30,000 and goes down to, we assume, 0. We have a point G halfway along, so this is representing the minutes. Okay. This is representing the number of people. Okay, I think that's what part A here is. Part A says the point G has coordinates 6, 21. So the x value, the y value. Explain what the 6 is. Well, 6 is the time after the match. Okay, after the match. And the 21,000 represents the people left in the stadium. People, excuse my bad writing, left in stadium. I probably could phrase that better. Okay, and I have it here on the next page. Why did I even say in my notes? I'm kind of wrong here. When I say 30,000, I should have said 21,000. I'll fix that after. But that's it. That's a fairly handy one. This seems to be worth 10 marks over part A and B. Okay. Now part B says it took 20 minutes for all of the 30,000 people to leave the stadium. Use this fact to write down the coordinates of the point W, which is on the t-axis. So this is W. So look, the x value all along, this is a trick that is often employed in coordinate geometry. T represents the x-axis, or it's on the x-axis. Okay, and at the x-axis, okay, y is always 0. Okay, now in this case, the y-axis would be represented by p. So this is the x-axis, this is the y-axis. So it might be 30,000, 20,000, 10,000, whatever it is. But this is 0. So all along this, y is 0. So straight away, I know that this value is 0. Now, if it took 20 minutes, that's the x value. So it's just 20, 0, which is fairly handy. Okay. Now that is, in a sense, easy. But if you were, like if you say if English is not your first language, or you struggle with reading, which is, lots and lots of people do, these kind of questions can be problematic. First of all, they're intimidating, but second of all, like there's lots and lots of words, and it's about a complicated scenario with a graph. Just take your time. Again, if you've read it 5 times and you're like, oh, why am I so like whatever? No, I mean, everybody should be reading it 5 times. Everybody probably is reading it multiple times, and those who don't are the ones making mistakes. Okay, so take your time and just give your best shot. Okay, sometimes the answer you think it is, you go, it can't be that easy, and we talk ourselves down, and we end up going down a different path. Okay, so part C has two parts to it. This is where we get into the kind of more algebra phase of it, but also like coordinate geometry and slopes, I'm sure. The equation of the graph can be written as this. So this is our linear model. So I know it's linear, okay? And a linear model will follow this general format. Y is equal to mx plus c. Now, sometimes you might see that as mx plus b in different maths things, but it's ultimately the same. Now, if I put what we have below it, it doesn't really look like that, okay? Because this x, in this case, is being represented by the t. So if I just rearrange that, put the t similar where the x is, in a way I'm just reorganizing them, okay? And now compare that to y is equal to mx plus c. Y is the p, t is the x, okay? So we're kind of comparing this to a more general form of any linear model. The important thing there is the m is minus 1,500, okay? So that's the slope, or the rate of change. The change of people is going down by 1,500, okay, a minute. So the negative is going down and the 1,500. Now the C value is sometimes called the y-intercept, and it's where your model crosses the y-axis, okay. So you can see from the graph, I flick back, okay, try to go for a clean version. Let's knock off that. That's where it starts, okay. Then you can work out the slope, and you could work out the slope by different methods. Okay, you could use the slope formula if we had to. We don't need to. We're given the model, and then we end up with the scenario playing out. Okay, so that's the y-intercept, and any equation of a line that crosses the y-axis. That if I said to you, where does this equation cross the y-axis? It crosses at 3. As long as it's one y equal to everything else, that number represents the y-intercept. Okay, so again, coordinate geometry. Now, let me clear off all that. So it says here, how many people were in the stadium 12 minutes after the match has finished? Now, I went down a whole rabbit hole there that I didn't necessarily need to forget in the question. There are two unknowns, P is equal to what, and T is equal to what. But we've just been told that T is equal to 12, okay? So this equation of two unknowns is now an equation of one unknown. All I have to do is swap out the t with 12 in brackets. I can put that through the calculator and I should end up with this answer of 12,000 people. If you can imagine, there's 30,000 people to start. After like 12 minutes, there's only 12,000 left. I can see that 12 minutes is a lot of time. People, trying to get out of a stadium, blah, blah, they're all moving and moving and moving. Okay. There's no reason why that number would be like suspicious. If it said like 12 minutes and it was like negative 400, I'm like, how can there be negative people? It might give me pause. Okay. Now I'm supposed to stay on the answer here. Part 2 says, explain what the 1,500 in this equation means in terms of the number of people in the stadium. Okay. So the 1,500 is the slope. Okay. Now again, I generally prefer to call that the rate of change. And ultimately, in like, I suppose I'm a science teacher, but in science, measuring change is what science does. If we can measure change in something and then try to understand it using a mathematical model or a graphical, whatever, modeling the behavior. If that behavior is predictable, we can use that in different scenarios to see what would happen in that situation. If we, let's say, can't measure something beyond a certain tolerance, we just physically can't do it. If we can maybe understand that that model is linear or quadratic or trigonometric or periodic or whatever, it's following a pattern that we can't test, but if the assumption is true, we should be able to create a mathematical model to represent what would happen, and then if it ever can be tested, we can ensure the model is working correctly. So mathematical modeling is a huge area of maths/science that is probably underappreciated in the learning outcomes of junior cert and leaving cert at the moment, but it controls a lot of our lives. Okay, we just don't necessarily realize it controls a lot of our lives. But ultimately, the rate of change is what we are trying to measure and trying to understand the world around us by looking at how the world changes. And in science, when we do something specific, we only change one thing and measure the effect on everything else. And then trying to understand the depths of this, maybe on a molecular level, and maybe if you go crazy in physics on the quantum level. Okay, but that's a bit more spooky. So for simplicity, and because it's easier to say, we often refer to it just as the slope. Okay, so the 1500 represents the change. Okay, it's a negative number because they don't ask us for the negative part of it, because the change is going downwards. There's 1500 less people in the stadium every single minute. So that's how many people can leave the stadium. And that's what I said in the last thing. 1,500 people leave the stadium every minute after the match is finished. Until there's nobody left, if you wanted to be more pedantic. But that's perfectly fine, and it's taken from the marking scheme. So question 11 then is finished, okay? I thought it was longer. Okay, I mean, if you want to copy the notes I'm working off, just send me an email at shanetroy@gmail.com. Like and subscribe to get access to more playlists. And I'll see you on question 12.